All right, thank you very much to the organizers for inviting me to give this review. I'll be telling you today about recent advances made possible by the Gaia mission in understanding the dark matter distribution in the Milky Way and how those can help us constrain dark matter models. So Gaia is the first large-scale, what I would call phase-space survey of the Milky Way's stars. It's been orbiting at L2 for about 5 years now, taking data. It's got another 5 to go, and it's on its third data release. I'll tell you what that means in a little more detail now. What you're seeing here in the main screen is Gaia's all-sky view of the Milky Way and its 2 companion galaxies, the Large and Small Magellanic Clouds. So what I mean by phase-based survey is that Gaia measures the full 3-dimensional positions and velocities of lots of stars. What that means in practice for astronomers is that you measure things basically in an egocentric coordinate system. So you measure the distance to the star, its line of sight velocity using the Doppler shift, and then its angular position and velocity. And Gaia measures all but the line of sight velocity for every star that it observes. And I'll show you a little bit more about how that works. So the basic idea I will illustrate with our closest neighbor, Prox Centauri, which is the star shown in this Hubble and in the background DSS image. So basically what you do is you take a lot of pictures over time of the same star, and then you line them all up using more distant background stars that you assume are far enough away that they'll have nearly 0 angular motion with time. And if you do that, you can see in the background that you get the star appearing to move across the field. And then if you look more closely, you'll see this sort of curly motion here with a period of 1 year. So the bulk motion across the field is the intrinsic angular velocity of the star, called its proper motion. And this curly motion that repeats itself is proportional to 1 over the distance to the star. That's the geometric parallax, and that's how we know the stellar distance. And so this is why it's taken Gaia so long to get such a complete and high quality catalog, because if you have less than a year of data, then you can't disentangle the parallax motion from the proper motion at all. But now Gaia's been observing for a few of these cycles for most stars. I'll just note that this is the closest star to us that I'm showing you here, and therefore the largest parallax signal, and it's a couple of arc seconds, which is a very, very tiny angle, like 1/200,000th of a degree or so. So Gaia does this measurement for a total of about 1.8 billion Milky Way stars. So for most of those stars, it measures all but the line of sight velocity, which requires taking a spectrum of the star instead of looking at its image. But then for a subset, it also has a spectrograph on board that measures the line of sight Doppler shifting of the spectral line to get the line of sight velocity. And that means that for this green histogram of stars in the Milky Way, which is a gradually increasing fraction of the total sample, we have the full 6-dimensional phase-space positions of these stars. So going back to this image, what you're seeing here is not a standard picture where you just take an exposure of the light coming from the galaxy. It's actually all 1.8 billion of those stars, the light that Gaia observes from them in a couple different bands assigned to the RGB channels of the individual pixels in this image. So 1.8 billion stars went into creating the image you see here. So what this gives you in terms of an understanding of our galaxy is far beyond what we had up until Gaia launched. So prior to Gaia, there was a survey called Hipparcos, and this tiny little dashed circle around the sun here is the sort of reach that Hipparcos had with the same quality data as Gaia does. Now with Gaia, we can make the same kind of measurements in this larger volume here, and measure the probably the hardest of the 6 components to measure, the 2 angular velocities, out to this distance. And so now we're getting dynamical information, positions and velocities of the stars over a good chunk of the galaxy, about 1% of all its stars. And this picture doesn't really even tell the whole story. You can just imagine Gaia is literally 1,000 times better than what we had before. And this has really transformed our view in the galaxy in the last 3 years since the first data release. Okay, so the reason this is important for dark matter is that the Milky Way is a series of laboratories for studying dark matter. What you're seeing here is obviously not the real Milky Way, since I have a picture of the dark matter distribution. This is a simulation of a galaxy similar in mass to ours. And so you see in the center is the main galaxy with the galactic disk. And this is a diagnostic of how dark matter and standard model matter are interplaying in this system. I'll refer to standard model matter as baryons in this talk because that's an astronomer speak. And you also, from the disk, get a connection to what the dark matter is doing in the local solar volume, which is where you need to know it to interpret direct detection experiments. You can also see these smaller galaxies, scattered around. Those are essentially different scales for testing dark matter. They have a different balance between baryons and dark matter in the galaxy and are often good candidates for indirect detection experiments. And finally, you see these long streams of stars here. These are tidal streams that used to be satellite galaxies that have been destroyed by the tides of the central galaxy. And these are very sensitive sort of gravitational antennae. They can tell you a lot about the dark matter's distribution radially out from the center, its shape, and the smaller scale structure of dark matter, especially in the regions out here where dark matter is the dominant mass component and is therefore less affected by what's going on in the center of the galaxy, which is a significant degeneracy for a lot of these experiments. All right, so how did I get that image on the previous page? This is a crucial step because the cosmological simulations that are going to reappear throughout my talk are the way that we can interpret what's going on in our galaxy in the cosmological context, which is turns out to be very important. So this is effectively just an initial value problem. We know the initial conditions from measurements of the cosmic microwave background. And we assume some model of dark matter, and that sets how much dark matter there is by its production in the early universe. So here's a simple example from a cold dark matter model. And then you take a little piece of these initial conditions and zoom in on it, populate it with a bunch of particles that let you discretize the equations of motion on the cosmological background. You assume something about the dark matter interactions. You use a computer to add gravity and time, and you get a prediction for what the dark matter should look like around a Milky Way mass galaxy. And this is a simulation that included only collisionless dark matter, where more correctly, the interaction between dark matter particles is only significant in the early universe. And so it only sets the total amount of dark matter in the simulation. So the mass and the cross section determine how much you get. The primordial dark matter temperature and the production mechanism sort of set the minimum mass of these little blobs that you see around here, which are called subhalos. This main distribution is the main Milky Way dark matter halo. And until recently, the working assumption here has been collisionless dark matter. But lately, people have started to relax that assumption and explore other dark matter theories and what they predict. So here are some examples for different sort of phenomenological classes of dark matter models. And so then the game is to take these predictions from the simulations and compare them to what we observe in the Milky Way, and thereby constrain or rule out different models. So the problem with this is that sometimes your observations can have multiple explanations. So I'll illustrate this with a classic, the missing satellites problem. So if you look back at this SIDM prediction, which includes a growing Milky Way galaxy in the middle, you can see that there's lots of these little blobs called subhalos around here. And the prediction, the number of those subhalos in this image is far larger than the actual number of small galaxies that are observed around the Milky Way. And so that's what people call the missing satellites problem. So you can fix this in one of two ways. You can either change the dark matter model to get rid of all those halos, which is an example here. So this is the number of halos as a function essentially of the square root of their mass. So if you increase the primordial temperature of the dark matter, then you get fewer small scale structures. Or you can add cosmic reionization and feedback from supernovae to your simulation And that keeps the smallest stuff from forming any galaxies in it and reduces the number of satellite galaxies as a function of their mass down to what we observe in the Milky Way and Andromeda and other galaxies of that mass scale. So the moral of this story, you can find these examples all over this field, is that the process of galaxy formation, which is what has all this stuff going on, links the dark matter sector to the standard model sector, primarily through gravity, which is a force that thankfully is relatively simple to simulate, unlike some of these other things. So the big question that people in this field have been trying to tackle for a while is how we disentangle the new physics, like what dark matter is, from stuff that we technically understand, like star formation and gas physics and whatever, but which is often a challenge to model, and links galaxy formation to the structure of dark matter in the galaxy. So Gaia helps with this a lot because it measures both the positions of stars, which tell you about the baryon distribution through the light distribution of the stars, and it measures the velocities of stars, which are what you use to infer the total mass distribution. So you can start to disentangle these two pieces by using the data that Gaia has observed in our Milky Way. And the cosmological simulations that I showed you before, which incorporate both sides of this study, or both sides of this idea, are the key, I think, to interpreting the measurements that we're getting from Gaia. We also, it turns out, need these types of simulations. Here's a movie of this simulated Milky Way forming, because Gaia has very clearly established that our galaxy is not a static system. It poses a lot of challenges for the standard dynamical models we thought we were going to use to map the mass distribution. And this has turned out to be a big theme of the discoveries with Gaia. You can see how dynamic this system is here, and it's fundamentally part of the cosmological context of the Milky Way. Mergers with other galaxies are ongoing, the disk is forming in the middle, and all of this stuff is happening, and Gaia was the first real hard evidence of this. So here's some examples of that. This non-equilibrium phase-space distribution in the nearby stellar disk was one of the first discoveries that Gaia made. This pattern that you see here is not an equilibrium distribution. Lately, there's been some evidence from gas observations in the Milky Way that the gas is making this sort of wave relative to the disk plane. And there's evidence that some satellite galaxies, which have been observed by Gaia, this one here, this is the discovery panel from Gaia DR2 data, are responsible for messing with the disk of the galaxy at the outskirts and the interior. And so these are both challenges to our models of an equilibrium Milky Way that were sort of the standard before Gaia, but also opportunities for new paradigms, right? The rate at which this disperses is proportional to the mass of the Milky Way's disk in the local stellar neighborhood, which includes both stars, gas, and dark matter, for example. And so since many of these disturbances are also fundamentally cosmological, it's important that we take that context into account even more in the Gaia era. All right. So Gaia takes this dynamical snapshot that lets us model both the total distribution and the stellar distribution of our galaxy from the same data set. And that helps us figure out what fraction of that mass is luminous versus dark. So this has given rise to many efforts to map the dark matter distribution of the Milky Way, and there is no way I'm going to get to all of them in this talk. So I apologize in advance if I miss your favorite one. But all these efforts are then connected in turn to tests of the model of dark matter, primarily through the kinds of cosmological simulations that I just described, which in and of themselves have undergone a renaissance in the last 10 years or so. So I'll try to highlight a couple of different ideas in the time that I have left. The first is just measurements of the local density. So pre-Gaia, the basic recipe was, you assume the Milky Way disk is in equilibrium locally, you apply the Jeans equations, you get an estimate for the total mass density. You take a census of the local stars, you model the amount of light they put out as a function of their mass, and that gives you the mass in stars. And then you do a radio survey, you estimate the local hydrogen gas mass, And then you just do some subtraction to figure out how much dark matter there is. And the standard assumption was that the velocity distribution of that dark matter is just a Maxwell-Boltzmann distribution with a width given by the gravitational potential in which it's sitting. So Gaia challenged this assumption right off the bat, not only through the examples I just showed you, but also because there's evidence for debris from an enormous merger about 10 gig years ago in the local solar neighborhood. So this is Gaia's view of the velocity distribution of stars. So the x-axis is the orbital motion of the stars around the disk, and then the y-axis is the quadrature sum of the other two velocity components. For disk stars, this is mostly random motion, but then you see that there's this other blue component that we think all comes from this merger. So this thing, if it's this big now, had to be about a fifth of the mass of the Milky Way. And that means it was a galaxy that came in with a bunch of dark matter. So if we still have significant stellar debris from this dark matter merger, or from this merger, then what about dark matter that could be significantly differently distributed than the standard assumptions? So this is work by Lena Nassib, and in collaboration with our FIRE collaboration of simulations. And the simulations here give us insight into which nearby stars are the best clue to what the local dark matter distribution is. So if all your dark matter is in equilibrium, which is this black line here in these histograms of velocity, then you can just find the oldest accreted stars, which we can do by looking at their abundance of iron, which is kind of like a clock. So the more iron it has, the later the star formed. And if you pick those stars out, they trace the relaxed dark matter distribution pretty well. But in the local dark matter distribution, you also have to account for these large mergers that brought other dark matter at slightly different distributions of velocity into the solar neighborhood. And it's a non-trivial part of the dark matter distribution. So you have to reconstruct these mergers in order to understand the full local dark matter distribution. And we have one of these in the solar neighborhood, which I just showed you. So if you apply the same sort of reconstruction technique, which relies on scaling relations between the stellar mass in a galaxy and its dark matter mass, then you find that the expected velocity distribution of the local dark matter is significantly different from the standard Maxwell-Boltzmann assumption. And this goes directly into the rate calculations for direct detection experiments via this factor of the velocity distribution divided by velocity. And so moving the peak of this to smaller velocity makes the constraint stronger for things with lower V-min and weaker for stuff at large V-min. And it changes the form of the annual modulation of the detection signal. So you can check out Lena's papers if you want more about this. Gaia can also let us measure the escape velocity better, and that's a better way to get the total mass, or another way to get the total mass locally. And this is basically because the escape velocity involves detecting the tail, the high velocity tail of the dark matter distribution, as you can see in a couple of these examples, and modeling it with a power law. And that gives you the escape velocity, which you can then use to get the potential. And then the potential gives you the total mass. So the more stars you have, Gaia has lots of stars, the more sensitive you are to that power law, and the better you can model it. You can see that in this paper, they modeled it as a function of distance from the center of the galaxy. And there's this weird divergence from what we expect, and that they think is probably non-equilibrium structures. All right, so that brings us to the total mass, which is really the number that normalizes our comparisons with cosmological simulations. And in particular, it's the overall normalization for the predictions of how much substructure there is in the galaxy, and therefore all of these other things that are sensitive to the dark matter model. And a factor of 10 in mass uncertainty is a factor of 10 in the number of subhalos at a fixed mass within a galaxy. So this is a first order systematic. So we know the mass of the Milky Way very well now, thanks to Gaia, within the inner 20 kiloparsecs, which is like this region highlighted in red. But there's a lot more dark matter out in the outskirts, and extrapolating from this region out to here is really complicated because the mass in dark matter just increases relative to the mass of baryons as you go further out. So the streams can help us here because they go far out into the galaxy and they consist of stars that are all on very similar orbits, which gives us little probes along different axes. So you can see that Gaia has really converged everybody on some mass here, but then as you go further out, you start to get a large, factor of 3 uncertainty in the total mass of the Milky Way beyond. Most of these estimates use either a model of point tracers orbiting in the system, like those satellite galaxies that I showed you, or they are models of single tidal streams. But tidal streams, if you model only one at a time, can be pretty subject to bias. We can do better with Gaia because not only does it observe stars in many different streams, but with 6-dimensional information, we can use the full power of Hamiltonian dynamics, including the action angle formalism, which is the natural framework for analyzing bound orbits. So rather than give you a lot of equations, I'll just show you a movie. Over here, you see a tidal stream forming in an invisible main galaxy in position. So after a while, here's another one. They get all wound up in position space. But over here, you can see what's happening in action angle space up here and in action space down here. And you'll notice that this is a lot simpler to deal with down here. So since individual tidal streams come from smaller galaxies than the Milky Way, they have a smaller phase-space distribution, or smaller phase-space volume than the total Milky Way available. And so that you get these small clumps, 1 per stream, roughly, in a larger action space. So if you see them in positions, they'll be all over the sky, all over the galaxy. But if you know something close to the best fit potential, you find that they're still clustered. This only happens in the correct potential. So what we've started to do is quantify clustering statistically and then use this as a figure of merit to model the potential. So this was a test using a cosmological simulation. And the black line is the real mass profile of the dark matter halo, and the red is our prediction from using the clustering of the streams as a whole. So this lets us model lots of streams at once, even if we don't know exactly which stars belong to which stream, because you can quantify the clustering with a statistic. So we've recently applied this to real streams for the first time, and here you see some of our results. You can see that these individual dots, which are the biases from fitting individual streams, can be very significant. But once you combine lots of the streams together, especially if you take this outlier out of the picture, then you start to get something that matches with fits from inferring the potential from the orbits of disk stars, which are these other lines that are shown here. This gray one in particular is from Gaia data. All right. So beyond the total mass, you can also look at the shape of the Milky Way's halo, and this can give you some information about the significance of dark matter self-interactions at late times and low densities. And it also is a good way to detect the impact of the crosstalk between the baryonic and the dark matter components of the galaxy. So Gaia has enabled a lot more attempts to measure the Milky Way's shape, and most of these are using streams because they're separate. They're especially sensitive to the shape of the galaxy. They start out on similar orbits, so departures from spherical symmetry lead to precession of those orbits in bulk, and precession of the plane that the stream is in. So here you see all of these measurements from this table summarized in a plot of minor to major axis ratio versus radius. They're all over the place, but they kind of seem to be rounder than the predictions from cosmological simulations. So the red band in particular is a series of simulations that include collisionless dark matter and hydro to form the galaxy. And they look a little bit less round than the measurements in the Milky Way. One conjecture is that including self-interactions could transport angular momentum more efficiently and round out the halo. But what we found when we went back and included the galaxy forming in the middle was that this worked in advance, or in the opposite sense. So the shape of the halo gets rounder when you include a galaxy because of the exchange of information between the two components.
Robyn,
And if
I'm
you,
sorry,
yeah,
this is Lisa. I just wanted to let you know that you have about 5 minutes left.
I thought I had 35.
I think we give you 25 as a 5-minute warning, and then
Okay.
you have a 5-minute question and answer session at the end.
Okay, cool.
Okay,
Sorry,
yeah,
thanks.
no problem.
Right, so, and you can see that there's a little bit of a difference in shape if you change the model of the dark matter, but it doesn't help you much other than to introduce more variability in the shape, since the since a significant cross section can let the dark matter respond better to the shape of the growing galaxy. So if you want to take a look, this is the galaxy that was growing in the middle of this SIDM halo, which is sitting down here in this thing. All right. The other thing that's going on that's a new opportunity for constraining dark matter models with the Milky Way that's brand new is the fact that they're merging with these two companion galaxies, the Magellanic Clouds. And these were, when they came in, the larger one is thought to have been about 1/10 of the mass of the Milky Way. So it has a significant influence on the galaxy. This is a relatively new development, and it may explain why it is that all these shape measurements are disagreeing with cosmological predictions for the following reason. So very recent work has shown that if you ignore the Large Magellanic Cloud in particular, when you model the shape, you get something kind of weird looking that starts to be less weird if you include a separate mass component for the LMC. And this, in turn, predicts a response in the dark matter due to dynamical friction that is very likely to be specific to different dark matter models. So here's an illustration of the wake and the dark matter distribution of the Milky Way created by this interaction in the context of a collisionless dark matter model. So this is a new opportunity to test different models with predictions. And we're starting to see some hints in the density anisotropy in the stellar halo. This is hot off the press from last year, that this is actually happening. But stay tuned, because this is a new avenue that's likely to bear fruit in the next 5 years or so. All right, in the last couple of minutes, I'll talk about the final thing, which is the small scale structure of dark matter halos, which is a good probe of the primordial dark matter temperature. So these are pretty powerful discriminations between different theories. As you can see visually here, the small scale structure changes quite significantly. And if there are lumps in the halo, then you expect them to disturb the tidal streams as they orbit in the galaxy every time a subhalo passes. So you can see there's one invisible dark matter subhalo there, and there's another one. And these can open up little gaps, or they can change the velocity dispersion of the stars in the stream by heating over time. And there are some tantalizing hints that this is the case. Here's an example of a stream that has clear gaps and like some substructure in it that you can model by these type of interactions. Gaia's role here was actually to very cleanly remove non-member stars, interloper stars, by selecting the proper motions associated with this stream. And that lets the gaps show more clearly. So it's very important. So then you have to interpret, what does this actually mean? How often do we expect this to happen in different dark matter models? And in particular, the interactions are influenced by not only the mass of the subhalo, but also its size. And unfortunately, the clean interactions that I showed you are often a little more messy when you try to account for the fact that there are many of these interactions over time. So this is because you get many of these interactions over the lifetime of one tidal stream. All these little red dots are all the subhalos that come within striking distance of this one tidal stream over time. And this is when you include a galaxy forming in the center and a self-consistent stream. So the central galaxy in a galaxy like the Milky Way is pretty good at eliminating substructures locally where the disk is, because the disk deepens the potential and increases the effective tides. So here is the ratio of the expected number of subhalos if you don't include the galaxy on the bottom versus if you do on the top. And the streams for which people have done most of their attempts to constrain this are located here and here, where there's a lot of this depletion going on. If you go further out, you don't have streams from globular clusters, which are very dense, and so they need to get further in for tides to disrupt them. But you do have streams out there from satellite galaxies, which are less concentrated. And so what we've been trying to understand is whether you can use these. I'll skip all this messy stuff.
Yes.
But I'll just wind up by saying that we are now able to start using our realistic test cases to quantify the expected rate of these interactions in different dark matter models. Thanks.
All right, thank you very much for your excellent talk. I'm going to encourage the audience. We have a few minutes left in the Q&A. If you have a question, you can write it there and I can read it out. In the meantime, there is one that was provided earlier in the session. Let me just read it out to everybody from Arthur Kozowski. How many spectra are really needed to get a statistically complete sense of the full 6-dimensional phase space distribution? In other words, how much work should we do on radial velocities before the scientific return becomes small for the dynamical measurements we care about?
That's a great question. So I think the best answer is to let the people that have designed surveys to follow up faint stars with Gaia proper motions, but no line of sight velocities from the ground. So part of the reason that Gaia doesn't observe line of sight velocities for faint stars is because you can do it more efficiently from the ground using multiplex spectrographs. And multiplex means it can take spectra from like 100 to 1,000 stars at a time in one field. So surveys that have come out recently have started to follow up on the order of thousands of stars. But eventually that number will grow with missions like WEAVE and DESI and Foremost to probably tens of thousands. And I think it's not so much the number of spectra that you have, but which stars you target. And so locally, I think we're getting to the point where we have enough of that information sort of in the local few kiloparsecs just from Gaia. But once we get further out, the spectra get harder and harder to get, but more and more informative because they then tend to be more in non-equilibrium structures like tidal streams. So I would advocate, and I have been advocating for the types of missions that will then target these faint halo stars, both through SDSS-5 spare fiber proposals and other things that are being planned for the next decade, like the Mauna Kea Spectroscopic Explorer. So I can't give you one number, but I think the number goes down as you get out, probably in a way that leaves the total observing time constant, given the fact that the distance makes the spectra harder to get.
Okay, thank you. That was an excellent answer to that question. Thank you again for your talk.